All right, so this is to supplement the class from October 2nd, 2019. So this is EML 3100 for fall of 2019. Yes. Okay, so we started a problem today in class. We said that we have 1 kilogram of air and the air behaves as an ideal gas. And it's a closed system all the way till Monday of next week. Then we'll start with open systems. And we have a bunch of values given. So we started this in class. And I'll finish this on Monday, but just in case you want to know how to finish it, then you can watch this, and then I'm going to go over the recommended problems as well. So again, this is not mandatory. So if you're watching this, you have something better that you want to do or need to do, you can just go ahead and do that instead, okay? All right, so we started in class and we said process 1 to 2, we have constant temperature expansion. So we see that on the notes. We're like, what is it? You know, we have expansion and the temperature remains constant. And we know it's expansion because we have that the volume 2 is 2 times volume 1. So when it expands, we would expect the temperature to decrease. But, you know, things aren't always the way we expect. So we probably have Q in there. Process 2 to 3, we have constant volume. And here, the pressure is increasing to 500 kilopascals again. So, well, I'm saying increasing, but again, we don't know what's happening to the pressure. I expect the pressure to decrease the same way I expected the temperature to decrease during the first one, but the temperature stayed constant, so we'll see what happens to the pressure, okay? However, when we did the PV diagram in class, we started that. In 2 other sections, we did both processes. In the other section, we just did 1 to 2. We see that from 1 to 2, I don't know how you can see this before this on my Mac. From 1 to 2, we have this over here because we have constant temperature in an ideal gas. So that has the behavior of PV constant. And we have expansion, so it behaves that way. That's it, okay? That means that the pressure will indeed decrease. Now from 2 to 3, we have constant volume, and this around here is where I stopped in one of the sections. So as I said, I'm gonna do this on Monday again. So it's a good review. It's like, this is ideal gases, so let's move on after that. You might get to see my new cats over there, okay? All right, so 2 to 3, constant volume, and the pressure goes back to the initial pressure. So we move up, all right, from 2 to 3. So it'll be something like this. Ignore my nails, okay? Where we have constant volume, so it's a vertical line and it's moving up. So the next thing that we should do is write down the equations for Q and for W for each process. So from 1 to 2, oh my god, you're gonna see it. From 1 to 2, that we have constant temperature. Delta U is 0 because delta U depends on temperature only, or U depends on temperature only. This is my new cat. Yes, isn't he perfect? Oh my god. You are not supposed to be here. Can't work like that. All right, so we have Q minus W equal to 0 for process 1 to 2. Then we have that work is PV, natural log of V2 over V1. Now, P times V is also MRT, okay? Which T? T1 or T2, because constant temperature. And V2 over V1 is also P1 over P2. Why? Because P1 V1 is equal to P2 V2, okay? So that's it. That's for work and Q. Now from 2 to 3, we have constant volume, so work is 0. And then we have that Q is U3 minus U2, okay? So in that problem, we want to find all these values, and we also want to find P2 and T3, which is what we're going to do on Monday. Now, for a problem like this, you might be wondering, so what do I do? Which method do I use? Constant specific heat or variable specific heat? The problem doesn't say anything, so we're going to use variable specific heat because that's the exact way. So that's what you're going to do, okay? So to find P2 and T3, if you want to do this, all right, you want to start doing it. I'm not going to show you my notes right now. Just show you from far away. You can pause it and see it. I forgot. So to find P2, because we have constant temperature from 1 to 2, we know from the ideal gas equation of state, if we manipulated that PV equals to MRT, that we're going to have P1 V1 equal to P2 V2. So that means that P2 is equal to P1 V1 over V2. We'll get that P2 is 0.25 megapascals. So if you want to practice this before Monday, great, you get it out of the way, okay? And from 2 to 3, we have constant volume. So for constant volume, we have that P over T is constant. And that's on the handout that I gave you guys. So it means that P2 over T2 is equal to P3 over T3. I'm going to show you this one over here. Okay? Excellent. Okay. That means that T3 is a function of that ratio of pressures and the temperature too, and we get that's 1,000 Kelvin. All right? And in order for us to use this, I need to use 500 Kelvin for the temperature because I use PV equal to MRT where T is in Kelvin. So I have the values of temperature, which we need. Let's see. We need them to find U anyway. The equation we have for Q is equal to W. It's just PV times natural log of V2 over V1. And that's also MRT times natural log of V2 over V1. That's important because now we can just use T, which is 500 Kelvin, R, which is 0.287 kilojoules per kilogram Kelvin, and M, which is 1 kilogram, and we can solve for work 1 to 2, right? We have that ratio of volumes, and that work 1 to 2 is 99.5 kilojoules, which is equal to Q. Okay? All right? That means Q equal to W. It means that as it is expanding, right? If we don't want the temperature to change, the microscopic energy inside won't change either. Someone asked me about this, and the pressure tends to be very, very low for an ideal gas. That's why we have the pressure much lower than the critical pressure. So, what was I going with that? So it's just very, very low. So it depends more on the temperature, which is very high. Okay. Now, that means that all the Q going in, it's not that it's not doing anything, all right? But it'll be equal to the work out due to expansion. Now, from 2 to 3, we just have Q2 to 3 equal to M times U3 minus U2, if it's in specific terms. So we find U at T2 and U at T3 from A17, all right? A17, not A to B. The values I have here for U2 and U3, I don't know if those values are from another table, because I did this last semester. Stop it. So the value, I can't handle this. The value that I have for Q over here is 399.5 kilojoules after I multiply by the 1 kilogram. But just make sure that you practice finding that U3 and U2 from the tables. Okay, so that's the one that we're going to do on Monday, and with that we finish ideal gases. Now if we take a look at the practice problems, just in case you want to start that before Monday, you should do that because next week we're going to do some new problems for open systems. Let's take a look over here. Just go over a few. Stop it. Just going to go over a few, okay? Find the compressibility factor at 300 Kelvin and 100 kilopascals. That's the first one for air. So what we're going to do over there, is find the critical value of temperature and pressure for air in table A1, okay? And you're going to find the reduced value of pressure and temperature, which is that value of T and P, or T divided by TC, and P divided by PC. That will be PR and TR, reduced values. You use those values of reduced temperature and reduced pressure. You go to a compressibility factor chart, can't talk, and you find the compressibility factor. I don't know what it's equal to. I'm just telling you what you have to do. Then for the second problem, we do compressibility factor of carbon dioxide at 100 Kelvin and 1 megapascal. Just by looking at that, carbon dioxide. So I don't know the behavior of it. However, 100 Kelvin, that's low. And 1 megapascal, that's really high. Actually, it might not be possible to calculate that. I need to check. Well, this sucks. I'm recording. I'm not going to restart this. But with those values, we might not even have gas, okay? So I'm going to solve that, and I think I did problem like this before, which was on purpose, because we had to be really careful. We have to think what is happening. These values, like this pressure is really high, this temperature is really low, so maybe this is outside what we discussed in class, but I'm going to look that up. All right, next one, number 3. Use the ideal gas equation of state PV equals to MRT to derive an expression for constant temperature process in terms of pressure and volume. So we know that if it's constant temperature, PV is constant. P initial times V initial is P final times V final. Then constant pressure process in terms of temperature and volume. Then if it's constant pressure, I have V divided by T for a process is constant. In a similar way, what did I say there? V divided by T. And then for constant volume process, then P divided by T will be constant. This is so helpful, okay? Then the next one, no. The next one, number 4, it says the ideal gas equation of state expressed that way uses the gas constant. So we're going to calculate that, just calculate that. And we're going to use 8.314 as the universal gas constant and the molar mass of air, which you can find from your table A1, which is 28.97, I believe, kilograms per kilomole. So those first few questions are not that bad. And question number 5, we want to find the change in specific internal energy change in U. If T1 is 1300, T2 is 300 Kelvin. So temperature is decreasing. All right, and U depends on temperature only, so I expect U to decrease as well. Using variable specific heat is just using table A17. Using constant specific heat at T average, we would find that at 800 Kelvin, we would find CV. Multiply that CV by 1000 Kelvin, which is delta T. And then the next one is a different way. It's using constant specific heat at 300 Kelvin. So we find that specific heat at 300 Kelvin, which I believe is 0.718 kilojoules per kilogram Kelvin. We multiply that by 1000. And we'll see that the value will be pretty different, or should be pretty different, when we compare it to parts A and parts B. Parts A and B. So sorry. Because that C depends on temperature, and we're finding it at a really low temperature, okay? Now number 6. Find the density of air at 350 Kelvin and 120 kilopascal. So there's no table for that. We find it using the inverse of specific volume. So we know that specific volume from the ideal gas equation of state is MRT over, RT over P. So that means that P divided by RT will be the density. We have the pressure, we have the temperature, we know the R of air, so we move on. Okay, the old exams, the solution is posted. I haven't seen them, so there might be some tricky ones there. I don't remember, except the multiple choice questions, answering and explaining. I don't think I have time for that. So 414 from your textbook. Let's take a look at that. It'd be great if you allow me to scroll textbook. Thank you. 414. It says a mass of 1.5 kilograms of air at 120 kilopascals and 24 degrees Celsius, which we have to change to Kelvin, is contained in a closed system, okay? The air is compressed to a final pressure of 600 kilopascals. During the process, heat is transferred from my system such that the temperature remains constant. Similar to what we saw, we compress it, we would expect the temperature to increase, but it remains constant, so we're going to have Q out. Calculate the work input during this process. So, let's see. All right, so this one we have Q minus W delta U. So we could use that to find Q. But we cannot use that to find W, or we should not use that to find W because Q is not given. Because this is a constant temperature process, then work is PV, natural log of V2 over V1. We have the two pressures. We would have to find or calculate the volume unless we use MRT, natural log of a ratio of pressures, which we can do as well, and then we don't have to do any calculations of volume. So that's an option. There was one of these problems that the solution was wrong, and I don't know if it was this one, so we'll take a look later. Now 4:57, I only have a minute left. Crap, sorry. 4:57, come on, where are you? Is it possible to compress an ideal gas isothermally in an adiabatic piston cylinder device? So if I say that Q is 0 and isothermal means constant temperature, that delta U is 0, can I compress it? Then no, right? Because if I'm saying that the temperature is constant for my system of an ideal gas, it means that the microscopic energy remains constant as well, okay? So it means that any Q going into it has to be equal to W going out, or W going in equal to Q going out. Now, I don't have time for more problems because only 15 minutes. So hopefully it was helpful, and I'll see you guys later.